Hello, welcome back to my 9th session of QNX awareness demo videos. In this session we will see how TRACE32 handles SMP systems. If you remember my first session, the introduction section, I showed you the board that I use. It's a small Panda board using an OMAP 4430, and this one has two Cortex-A cores within the chip. We can also check the system inside our terminal window to QNX. We say pidin info. You can see that we have two processors here. Each of them is a Cortex-A9 Pico CPU. So we have an SMP system where QNX handles both cores, and the processes are running on either core depending on where QNX schedules the process. Now first we start debugging the process as usual. You already have seen this several times. We start with QNX, process debugging, debug process on main, our standard example which is cf_g. We send it to the terminal window, OK, and we start debugging. Searching for the symbol file, which is in this directory. We have it here, and here we are. Let's do this here, mode, and you can see we stopped at the main entry point of cf_g. Let's first go until the while loop within this process, which is here. So let's set a breakpoint here and say go. Now I'd like to show you already the first SMP indication. If you go down to the status line of TRACE32, you will see at the left side where we halted, then the process in which we halted. Actually it is the thread, not the process. And then you can see this small 1, which is already an indicator of the CPU that we are currently halted on. This one shows the CPU number that caused the breakpoint to halt. If the system runs onto a breakpoint, the complete system halts, not only one CPU, but all CPUs that are handled by the SMP system. So running on the breakpoint, regardless which CPU runs onto the breakpoint, causes both CPUs in this case to halt. So the system is really halted. The debugger then automatically changes the focus to the CPU that caused the breakpoint. And in this case it was CPU number 1, so we are working on CPU number 1 in this case. Now if we right click onto that field, you can see a small menu with cores, and here you can select the cores that are available in the SMP system. Let's switch to core 0, and you can see that the data list window changed to the place where the core 0 is actually running. It is somewhere different, so maybe some other process, maybe the kernel, but of course the CPU 0 does something else. In this case actually the core number 0 is also running within our cf_g application, but currently it's running inside a library routine. What's interesting is the display in the status line of TRACE32. You can see that we are in the second thread of cf_g. If we switch back to core number 1, we are back to the main thread of cf_g, and you can see where we halted at the breakpoint. Now please have a look at the background color of the data list window, or on other windows as well if we open the register window. So watch the background color, which is light green here in this case, and if we change the core to core number 0, you can see that it's a light red. So the color changes anytime the core changes, so that you have a quick overview at which core the focus of TRACE32 is currently set. So changing the cores, and you can see that the color changes, and of course as well as the data list window, which shows the current PC of the current core, and also the registers of course are changed to the registers of the core that you select. Now I'd like to show you the threads window of QNX, which is also special in SMP systems. Let's scroll down until our CFG threads. Here you have a CPU column within the threads window, which shows you at which CPU which thread is running. So, and you can see that, for example, the main thread of CFG is running on core 1 and the second thread of CFG is running on core 0. So we have a quick overview which thread is running on which core, but keep in mind that this may change while QNX runs. QNX may change the affinity of a thread to a core while it runs. So this shows the current state at which core which thread runs. Now if you remember, we saw cores here in this status line, and in the thread window it's called CPU. Now there's a difference between CPU and cores. In TRACE32 the terminology is the CPU is the complete chip that you use. For example, in this case, if you open a CPU system setting, we have a CPU which is called OMAP 4430. So the terminology of TRACE32 says that a CPU is the complete chip with all cores within. And then in the terminology of TRACE32 again, a core is then the specific core with a specific set of registers. Now in QNX it's a little bit different. In QNX, CPU really means the core. And because the thread window is more dedicated to the QNX terminology, so inside the thread window the CPU means core. So it's a little bit confusing, but I hope you can get it that this CPU means the terminology of QNX and this core is the terminology of TRACE32, but actually those refer to the same object. Okay, let's close that one. Now let's add a breakpoint into the helper thread of CFG, which is a known thread that CFG uses. View symbols, browse functions, let's go to CFG and the helper thread, and we set a breakpoint into the while loop here as well. Let's close that one. Let's move that one down to show you actually the changing. Let's open CFG window with the threads. And the register window. And now if we say go, every while and then the breakpoint changes from one thread to another. And you can see by watching the background color which CPU is running, and by watching the star which thread is running. And you can see that both is changing every while and then. But TRACE32 automatically changes the focus of the debugger to the core that actually caused the breakpoint to halt. Of course you can change the focus of the core at any time you want manually by switching the core numbers. Switch to core 0 and switch to core 1. So the actual implementation of SMP support in TRACE32 is that way that you as a user don't care about that it is an SMP system. You are debugging your application, you are debugging your threads, your libraries, whatsoever, without ever thinking of that you have an SMP system. The debugger itself takes care of everything that's down there and hides the SMP system from the upper layer. Of course you still have the possibility to manually edit the individual cores, but usually if you're debugging application you don't care about the cores. So to sum up the SMP support, using the SMP support you have control over each core that is used in the SMP system. You can edit each core and you can look at each core, but when debugging application TRACE32 tries to hide the SMP stuff from you so that you can concentrate on debugging your application without even thinking of that it is an SMP below there. Now that's it for SMP systems. In my next video I will show you how to do a performance measurement of applications with TRACE32. We will first have a look at a dynamic performance measurement, which you can do with each debugging system, and later on we will have a look at performance measurement with the real-time trace systems, where you need actual a real-time trace for being able to do that. So stay tuned, it will remain interesting for you. See you in the next video.